Hello and welcome to the BA 2300 review. In this set of slides, I'm basically going to cover what was gone over in 2300, but mostly as it pertains to what is going to be in 3400. The first thing we'll look at real quick or go over is types of distributions. So with types of distributions, you've got skewed, normal, and kurtotic. So positive skewed distributions are one where you've got a lot on the left and then it kind of trails off to the right. Normal distributions is where it's clustered around in the middle correctly, and then negative distributions is a long tail to the left and then nothing on the right. The way I always recommend doing this, and it's always a little bit amusing because I can't draw, is to draw a cat face. So we've got a very poorly designed cat face here, and the direction the tail goes is whether it's positively or negatively skewed. So positive is to the right, this tail goes to the right. Negative is to the left, so the tail goes to the left. Kurtotic or kurtosis is how peaked the distribution is. I'm not going to ask questions about specifically here, but you can have ones where it's all clustered in the center, or you can have ones where it's really spread out. The reason I bring these up is because the type of distribution you have can decide what type of test you're going to use. So in 3400 we're going to cover a whole bunch of tests, and certain distributions that are highly skewed will end up using different tests. The next thing is a type of variable. Again, nominal, ordinal, interval, ratio. Nominal is just names, it's just categories. Ordinal, all that matters is the order. Interval, now the order matters and the distance between each specific point is constant, but 0 doesn't have any meaning, whereas ratio, again, the order matters, the distance between each specific constant is the same, it stays constant, but 0 is the absence of. Why do we include this? Because the different type of tests you do, again, are going to be dependent on what you have here. Ordinal tests are going to use the median, which is going to be more non-parametric tests. Interval and ratio, they use the mean, those will be parametric tests. What non-parametric and parametric means we'll come back to later. As well as discontinuous and continuous variables, those will help determine what variable you do. Next thing is central tendency and variability. So you've got the mode, the most common, the mean, the average or the balancing variable, the median, the middlemost variable, and then you've got that central tendency for variability. You've got the variance and standard deviation that go with the mean, and you've got the range and interquartile range that go with the median. And again, this is going to come up whether you're doing parametric statistics or non-parametric. Not too much now that you have to know what that, just know that parametric statistics, we use the mean. Non-parametric, we use the median or other different things that are not the mean. And essentially what it comes down to is the power of the test. So like I said, we'll be doing we'll cover a lot of different tests this semester. And one of the things that's important is power of a test, or how strong a test is, how good a test is, how well the scientific community views a test. Tests with more power are better. However, if you use the wrong test, it loses all power. So if you've got a variable that's a ordinal variable that you should be using the median. First of all, parametric tests are more powerful than non-parametric. But if you've got a ordinal variable and you use a parametric test, use the mean, it loses all meaning. It loses all power. So in that case, you want to do the most powerful test you can given the circumstances. So that's why there are tests with less power, like non-parametric tests. That's why we do those, is because there are situations where they are the most powerful test you can do given the situation. This slide is the basic stuff that you should know how to do from 2300. Now, there's a little bit of this to cover in the first set of slides, but let's just go through this real quick. I don't want to spend too much time on this. N is the number of participants. There are 7 participants, so N equals 7. The sum of X is going to, so this is the sum of X, we're going to add all of the X's together. So we have 35. So this is equal to 35. The mean here is going to be the sum of X, so it's going to be equal to the sum of X divided by N, so it's going to be equal to 35 divided by 7, or 5. And circle your answer. We are not taking exams on paper, so it's not as big of a deal, but one of the things, if you're taking stats exams on paper, just circle your answer. Next, we have the variance. So the variance is equal to the sum of squares divided by n. If this had a hat on it, so if it was s hat squared, it would be equal to the sum of squares divided by n minus 1. I am not too picky there, so if you get to situations where you should be using n minus 1 or n, I'll typically allow both answers. So, but now we need to know what sum of squares is. So sum of squares, let's come up here, sum of squares, there's going to be 2 different ways to do this. It's going to be equal to the sum of the x minus the mean, so the x minus x score minus the mean squared. So in that case, you would take each x score over here, you would subtract it from the mean and square it. And then after that, you would sum them all together. That is what's called the definitional formula of sum of squares, because it is the sum of the squared deviations from the mean is basically what it is. There's actually an easier formula for sum of squares, though. That is, when I say easier, I mean it's easier to computate because you do not have to take each value from the mean. And that is going to be the sum of x squared minus the sum of the x's, that value squared, divided by n. So in this case, there's less to do because you can just square each x value, then take your summed x's, square it, and then you just divide by n. So let's take each of these here. Now we're going to take each of these x scores and we're going to square them. So we get 9, 4, 49, 36, 16, 64, and 25. Now we can sum all of those together. What do we get? This should be quicker for me to figure out because we have 190, 203. That seems wrong. While I'm doing this lecture, I'm just going to pop up a calculator. I'm not in the mentality of stats right now, or otherwise I'd be able to do that in my head very, very quickly. But we have, bear with me, sorry about taking an extra second. It's 203, so I was right. So we get 203 there. So this is going to equal, so sum of squares, we'll put it up here in the top. The sum of squares equals the sum of x squared minus the sum of x, that value, squared, divided by n. So what we've got here is 203 minus 35 squared divided by 7. 35 squared is 1225. So we have, and then that divided by 7 is 175. So it's going to equal 203 3 minus 175, or this is going to equal 28. Then your standard deviation here is the square root of your variance, so it's going to equal the square root of 28. And I won't even pull up the calculator for that, but you would normally calculate that. I prefer in this class that you calculate to 2 decimal places. All intermediate steps should be to 4, and then your final rounding should be to 2 decimal places. That'll be the case for exams. On homeworks, it will tell you how many to round to. But always remember to round to 2 more decimal places than your final answer on intermediate steps. So let's say this 175 up here had actually been 175 with decimal places. Then round to 4 decimal places if the final answer is rounded to 2. The next is the median. Over here we've got the median. I know there's a lot of stuff here, but to do the median, first thing you need to do is put these values in order. So what do we have? I'm going to put it down here. We've got 2, 3, 4, 5, 6, 7, 8. They're in order, so we've got the median. The median is the middle value, and in this case it's going to be a 5. Another way to calculate the median is to do n plus 1 divided by 2 and count that many ranks up. So n plus 1 divided by 2 ranks. In this case, our n is 7, so 7 plus 1 is 8. 8 divided by 2, it's going to be 4 ranks. So we've got 1 rank, 2 rank, 3 rank, 4 rank when we talk about ranks. Or position. Another way to say it is position, but I like to call it as ranks just to differentiate it. So it's the 4th position or the 4th rank, so you get that 5 there. Quartile 1 is going to be n plus 1 times 0.25 ranks or position. So in this case, n plus 1 is 8. 8 times 0.25 is 2. So it's the second one. So in this case, quartile 1 is 3 here. Quartile 4 is n plus 1 times 0.75. So in this case, it is going to be the 6th rank. So that is 7 here. So quartile 3 is 7. Interquartile range is going to be the 3rd quartile minus the 1st quartile. So quartile 3 minus quartile 1. In this case, it's 7 minus 3, so it's 4. And then finally the range here, I know I've covered this mostly up, but the range is the largest score minus the smallest score, so in this case it's 8 minus 2 is equal to 6. A lot going on this slide, but this is the basics of everything you need to know for the rest of the semester. There is nothing we will do that will get more complicated than this. I know there was some stuff in Stats 1 where you had to do factorials, things like that. As far as I remember, we're not even going to cover factorials. Everything on this slide is the extent of what we're going to do, except there's going to be formulas that are going to be a little bit more in depth doing what we've got here, or more steps, but it's still going to be what is here. The next is z-scores. So for z-scores, very simple things. We're not going to cover it too much, but just so given a mean of 50 and a standard deviation of 5, what is the z-score for 40? Well, if you remember the z-score formula, z equals the x minus the mean divided by the standard deviation. So here we've got a z-score of 40, so this is going to be 40 minus the mean of 50 divided by the standard deviation of 5, so we end up with negative 10 divided by 5, or negative 2. So the z-score for a score of 40 is negative 2. 65 on the other hand, it's a raw score of 65 minus a mean of 50 divided by a standard deviation of 5 is equal to 15 divided by 5, or 3. So your z-score there is 3. Then we covered probability. I am not going to talk too much about probability here. What you see on the slide is blank. The reason the slide's blank is because I'm not going to go into probability here. I will say there was a reason for going over probability, and that is because probability is the step between descriptive statistic, that mean, standard deviation, things like that, and inferential statistics, which is all these tests will be starting with this week or into next week. And basically what that is the probability is used to determine error. So when you get to chapter 9, we'll talk about type 1 error and type 2 error and how those are calculated, and those will basically be calculated based on probability. So that's why we covered probability there. In chapter 5, covered univariate, so looked at things like expected value, looking at the mean, looking at variance, looking at basic different things with probability there. Chapter 6 looked at bivariate and covered a little bit there of covariance and correlation, which we'll actually come back to in the last couple weeks. So some stuff there that we'll come back to and get to different ways to calculate and more of what they mean. Then you in chapter 6 looked at the normal probability distribution and looked at how that worked, and looked at the empirical rule. And the normal probability distribution is basically what allows us to do parametric statistics. So where does that parametric come in? That parametric comes in with the distribution being symmetric, the distribution being with the empirical rule applying, where basically so many values are within a standard deviation of the mean, so many values are within 2 standard deviations of the mean, etc. beyond that. Then looked at the mean and standard deviation of the normal probability distribution, or the standard normal probability distribution. I will probably put this on the first test just because it's so important. What is the mean of the standard normal probability distribution? The mean is 0. What is the standard deviation? The standard deviation is 1. And the z is the number of standard deviations from the mean. Why is this relevant? Because when we do our z-tests later, and that's not calculating a z-score, that's doing a z-test for the statistical z-test, we will use the standard normal distribution, probability distribution, and this standard deviations from the mean as our method of hypothesis testing. Then we talked about the central limit theorem. The central limit theorem is really important because to do parametric statistics, as I keep saying, you need to use the mean, but there also are, every single test you do in statistics, there are assumptions that must be met. These assumptions are various different things, like one of them is that you've got a normal distribution. We talked about that on the last slide, standard normal distribution, but you need to have a normal distribution to do many parametric statistic tests. There is things you can do though. One of them is you can apply the central limit theorem, and that is basically that as sample size increases, so once sample size gets to a sufficient point, you can assume that the distribution of the sampling distribution of the mean is normal. So as sample size becomes sufficiently large, the sampling distribution of the mean is counted as normal. Then there is point estimation. Point estimation is basically where you started statistical inference in the last few chapters of Stats 1, and that's where you'll essentially take and use the mean of the sample as an estimation of the mean of the population. So your mean of your sample. It's the estimation, or it's the point estimator of the mean of your population. And this is an important value, but it should also be noted that because of things like sampling error, which we'll come back to, because of sampling error, you can't use this as your only value. You have to look at it more in terms of a spread around that point estimator. We talked about a little bit already with the central limit theorem, but the sampling distribution of the mean, it's a probability distribution of all possible sample means. So if your population is, let's say, 30 students in class, and your sample is 10 random students, your sampling distribution of the mean would be all different possible samples of 10 students that could be collected from the class. And if you get a sampling distribution of the mean of the sampling distribution of the mean is the mean of the population. The standard deviation of that sampling distribution of the mean is referred to as the standard error of the mean, and it can be calculated by taking the standard deviation of your sample and dividing by the square root of n. And this will come back up later in our statistical tests that we do later. This is important. As far as proportions go, and I spend less time focusing on proportions than I do means, but as far as proportions go, you've got the standard deviation of the proportion can be calculated using the formula here, and we'll actually come back to this later when we look at correlations, because a proportion is in a way a correlation, or it's very similar to a correlation. So this formula that we have here for the standard error of the proportion is a formula that we'll use later when we look at correlation and regression. As I said before, one of the things that's important is you don't just look at the point estimator, you need to look at an interval around it. And this is what is referred to in statistics as a confidence interval, or an interval estimate. I will often say confidence interval. Your book uses interval estimate. So basically what you're looking at here is you've got your point estimator, your sample mean, and then you're going to take that and add and subtract a margin of error. As I said before when I was talking about the point estimator, one of the issues is that you are going to have error. If I take a sample of 10 random students out of 30, those 10 random students, the average of those 10 is very unlikely to be the exact same as the average of the 30. Let's say we were doing height. The average of the 10 from the sample's height is unlikely to be exactly the same. What is going on there? That is error. That is what's called sampling error. And this, when you're doing a confidence interval, you're basically accounting for that. You're using a probability to account for the error in sampling error as well as other controllable errors like that. So the purpose of the interval estimate is to provide information about how close the point estimate is to the value of the parameter. And the more confident you want to be with your margin of error or your interval estimate or your confidence interval, let's say you want to be 99% confident in your interval there, then the wider your interval will be. Whereas if you're 90% confident, you're less confident, that's going to be a narrower interval. So looking here, the interval estimate, the confidence interval, the formula you have here, it's going to be the sample mean plus and minus, and this is in a case where you know the standard deviation. So this is something that's going to come up quite a few times throughout the rest of throughout this semester, throughout 3400, is whether or not you know the population standard deviation. So that's what this is referring to here, is the population standard deviation. If you know the population standard deviation, you can typically do z-tests. This is, again, one of those assumptions we're talking about. So if you know the population standard deviation, you do a z-test. If it's unknown, like it typically is unknown, you'll do a t-test. That'll be on the next slide. But what is this confidence interval? So we've got our sample mean, plus and minus our critical z-value. So it's our critical z-value at our alpha divided by 2. The alpha in this case is 1 minus our confidence interval level. So it's 1 minus our confidence interval. And then you take that, and on the z-table, you'll get the value for that. I can tell you right now, just about everything you're going to do in here is going to be 1.645 or 1.96 as your 2 z critical values. But we'll come back to that later. As far as when we're looking at the t-test, when the population standard deviation is unknown here, it's very similar, but in this case, it's your sample mean plus and minus now your t critical value that you get from the t critical chart times the sample standard deviation divided by the square root of n. And this is something that we will go over more later, and it will come back into play. The final one I want to look at is the confidence interval for a population proportion. Again, I don't spend as much time on proportion, so as far as this goes, there's not too much here other than it's always going to be a z-test for proportion. So you're going to have your average proportion or your proportion from your sample plus and minus the z-score for the z-critical score, and then that is going to be time multiplied by the square root of your proportion times 1 minus your proportion divided by n. Very simple stuff. As it becomes relevant this semester, I will go over this more. That is all for the review. If you have questions, if for some reason you didn't take 2300, you took a different class at a different place, or it's been a long time since you've taken 2300, and what I went over here is still confusing to you, go ahead and reach out to me. I can get you access to more resources and we can get you caught up. I don't want you to go into the semester behind. When you go into Chapter 9 here, which will be available after this, and next week, when you go into Chapter 9, start looking at that, and if you are confused, contact me as soon as possible. Thanks, come on back.